Assalamu alaikum. I welcome you all to this lecture of capacitance of the transmission line. So in this lecture we'll see how the capacitance of the transmission line has to be calculated. Let us say we'll start from here. Let us say we have a charge plus Q and we'll assume a Gaussian surface, a cylindrical surface whose radius is x from the center of this charge. So we'll use Gauss law to first calculate the electrical field at the point which is at distance of x from the center of this charge. So we know that from the Gaussian law that closed integral over the surface, that is E dot ds, will be equal to charge encircled divided by the epsilon, where this q dash encircled is the charge encircled by the this surface, Gaussian surface. This is actually q dash. So we have here chosen the cylindrical surface as Gaussian surface. So the surface area of this will be equal to 2 pi x into h, where x is the length of the conductor. So when we open this up, it will be E dot 2 pi x into h, since E will be constant at this surface because it is at a distance of x at every point, so it will be constant, and the direction of E will be outwards at every point. It will be in the direction, the area vector, and this E will be parallel to each other. So E dot this ds will be equal to E ds cos of theta will be equal to cos of 0, that will be equal to 1. So it will be equal to E into ds, where ds is the 2 pi x into h. Finally, this E will be equal to q divided by h divided by 2 pi x into epsilon. I have deliberately done this just to make it q dash by h as denoted by q, where q will be equal to q dash by coulomb per meter. So the total expression for the electric field will be equal to this q divided by 2 pi x into epsilon. This will be volt per meter square, because this q will be equal to q dash by h, that is coulomb per meter. So we know that electrical field has the units of volt per meter. So here charge is coulomb per meter, it should be volt per meter square. So actually I just want to make it sure that will start from calculating electrical field, and then we'll calculate uh, voltage and charge relation. Finally we can get this ratio of the charge to voltage, will get the capacitance. But first we should be ensured that to find out the electrical field. That is why I have started here calculating the electric field. Now by calculating the electric field, we'll see what is the potential difference between 2 points. Potential difference between 2 points due to charge. This is the charge. We'll try to find out the potential difference between point P1 and point P2. Let me zoom a bit so that it will be slightly clear to you. Okay, so we need to find out the potential difference between this point P1 and point P2 due to this charge. So what we do, we simply integrate this electrical field between these 2 points, and these 2 points will be at a distance of d1 from the center of the charge, and P2 will be at a distance of d2 from the center of this charge. I have deliberately chosen the different points. They are not collinear to the charge. You can see this is charge, this is P1, and this is P2. They are not collinear. They are at different points. It is because we can take any point and try to find out the potential difference between these 2 points. If I have taken this P2 at this point, I might have restricted our you can say chosen path, because in that case, if the point would have been away from this point or at any point without this point, so you may thought that it might be difficult to calculate the potential difference. So in this case, you can see these two surfaces, you will see they are the equipotential surface, and we know that the voltage at the equipotential surface will be same. So the voltage at this point or at this point or at this point will be same. Similarly, the voltage at this point, at any point at this surface will be same. So potential difference between this point and this point would be same as the potential difference between this point and this point. That's why I have chosen different points. And by showing you the equipotential surfaces, you will be sure that the potential difference between this point and this point will be same as the potential difference between this P1 and P2. Let us use this electric field expression that we have just derived, and we'll put that over here, and we will get the value of the voltage difference between point P2 and P2. So it will be E dot dx. E dot dx, since we are going from this way to this way and then this way. So this is the path of integration. We can say that from this point to this point, we can have directly gone to this from this point to this point. In that case, the calculation of potential difference would have been slightly difficult. So when you go from this point to this point, it will be very easy, because in this case, the tx will be the change in the displacement from this point to this point, and the electric field in the same direction, so that their dot product will be their dot product will have a their dot product will be equal to 1. That means E dot dx will be equal to E dx cos of theta will be equal to 1. And from going from this point to this one, there will be no potential change, or there will be no work done from going P to P2. So putting the value of E is equal to Q divided by 2 pi x into epsilon into dx square. Q is the charge per unit length. When we integrate it, this is constant, 2 pi epsilon is constant, it comes out to be dx by x. When we integrate it from d2 to d1, it will be equal to ln of d2 to d1. Volt per meter. Again, it will be equal to volt per meter square, not volt per meter. Please make a correction over here. So this is how we can calculate the potential difference between 2 points. Actually, if you remember, in calculating the inductance, we exactly try to find out the flux linkage between the 2 points, because flux linkage, when we calculate, after that we were able to calculate the inductance by simply dividing the flux linkages by the current. Here we will first try to find out in every derivation the voltage difference between 2 points due to the charge, and then by calculating the ratio of charge to voltage, we will get the capacitance of the line. So we'll use the same thing over here. Capacitance of the single phase two wire line. We know that capacitance will be equal to charge per unit voltage, or charge by voltage. In capacitance calculation, we will first derive the equation for Q and then divide it by V, so that we can find out the value of C. I have just told you what we do for this case. So moving ahead, let us try to use the same process to find out the uh, capacitance of single phase two wire line. Let us say this is one wire, and that's wire A. This is, or we can say, conductor A. This is the conductor B. They are displaced from each other by a distance d. It has a charge QA and this has a charge QB. The radius of the conductor A is R1 and the radius of the conductor B is R2. So using the above equation, we will first calculate the potential difference between two conductors A and B due to the charge QA. That means we need to find out first, we need to identify the 2 points where we need to find out the potential difference. We'll find out the potential difference between charge A and charge B. That means we'll use the distances from the surface of the charge A to the surface of the charge B. That will be the potential difference between these 2 points. One more thing that you need to be sure, that in case of an inductance, we first calculate the internal inductance, because flux is linked inside the conductor as well. That means magnetic field is present inside the conductor as well. But in this case, since we are calculating the capacitance inside the conductor will be 0, because it is a conductor and we know that electric field inside a conductor is 0. So we need not to calculate the internal capacitance of a conductor. So when we calculate the potential difference between point, let's say, surface of this, that is, if the origin is the center, that is at the point of R1, to the surface of this, that is up to D. Actually, it should have been D minus R2, and I told you in the previous classes that we can approximate that distance to be equal to D. So that means the previous equation which we had used, that the VAD will be equal to some constant ln of d2 by d1. So here d2 will be equal to the distance, the second distance up to which we have to calculate the potential difference, because the starting distance will be the surface of R1. So it will be d2 will be equal to d. So similarly, sorry, this d1 will be equal to r, because starting point is the surface of this conductor and the end point is the surface of this conductor. That means its end point will be equal to, or d2 will be equal to d. So by using that equation, that means VAB1, the potential difference of between the surface of this and the surface of this due to charge QA will be equal to QA divided by 2 pi epsilon ln of d by r1 volt per meter square. So it will be due to QA. Similarly, potential difference between the conductors when we move a unit charge from the surface of the conductor A, that is from a distance of d. Now the charge is this, and the point at which the potential difference has to be calculated is again the same, but now the first point will be this, and it is at a distance d from this point. The second point will be surface of this, that is the R2. That means now d1 will be equal to d and d2 will be equal to R2. So distance of d from QB to the surface of the conductor B, that is at R2. So d1 will be equal to d and d2 will be equal to R2. So the voltage due to charge B will be equal to VAB, its charge divided by 2 pi epsilon ln of R2 by R1, because D2 is R2 by D volt per meter square, again due to the charge QB. So total voltage difference will be the summation of two voltage drops, that is QA divided by 2 pi epsilon ln of D by R1 plus QB divided by 2 pi epsilon ln of R2 by D. Since we know that it's a single phase two wire system, in this case the two wires will have the same charges and definitely will the opposite charge. So that means QA will be equal to minus QB. So replacing this QB equal to minus QA, we'll take that out. It will be equal to QA divided by 2 pi epsilon ln of D by R1 minus ln of R2 by D, that is this. So consuming this minus into this ln, it will reverse, or we can say we will have to take the reciprocal of this argument of this ln, so it will be plus and then ln of d by r2. Now we know that ln of a plus ln of b will be equal to ln of ab, so these two arguments of these two lns will be multiplied. So qa divided by 2 pi epsilon remains as it is, ln of multiplication of this argument and this argument will be d square divided by r1 r2. So taking this square to this side, because when we know that the power will be multiplied to this in case of ln, so I have written that 2 over here, 2 qa 2 pi epsilon. So since we have taken this 2 over here, this has to be square rooted, because we have to take the square of whole the term, so this will become the square root. So finally this 2 and this 2 will cancel out, it will be equal to VAB will be equal to QA divided by pi e ln of d by square root of r and r2 volt per meter square, or CAB will be equal to, I have written the relation a little bit weird, it should have been QA divided by VAB. Please try to modify this. It is not VAB by QA, so it is QA by VAB. So when we find out QA by VAB, it will be equal to pi e divided by ln of d divided by R1 R2. If R1 is equal to R2 is equal to R, which is usually the case, that means the radius of the two conductors will always be same. So in that case, this R1 R2 will be replaced by R square, and square root and square will cancel out. It will be equal to pi e divided by ln of d by R. Now this is the correct unit, will be farad per meter. Now we have calculated, this is the capacitance between the two phases, that is two phases of A and B. So we have shown it like this. So this is positive, this is negative, and this is the capacitance between these two. You can see we're going from positive to negative. There must be some point which has a zero potential difference. So that has been shown over here, and we know that the zero potential difference is a point we call it as a neutral. So there must be two capacitances between this CAN and CBN, that's the capacitance of conductor A and the neutral point, and capacitance of conductor B in the neutral point, and we're always interested in the per phase capacitance rather than the actual capacitance between the phases, that is the capacitance of the phase to neutral. So since these two capacitances are in series, so this is the equivalent capacitance of these two. That means the CAB will be equal to, or we can say the CAB will be equal to CAN by 2. Since these capacitances, they are at this point is at the center of these two conductors, they have the same charge and the same radius. So CAN will be equal to CBN. They will be same in magnitude. So we can say CAB will be equal to CAN by 2, because series, when the capacitors are in series, their overall capacitance will decrease, and we know that these two capacitance have the same value. That means the equivalent capacitance will be equal to CAN by 2, or CAN will be equal to 2 times CAB, or CAB we have calculated pi e divided by ln of d by r, so CAN will be equal to 2 pi e ln of d by r farad per meter. So this is the calculation and derivation of the capacitance for a single phase two-wire system. Similarly, you can go to find out any type of capacitance in any configuration, but I will not go into the derivations of it. I will directly write down the formulae which will be used, and they are almost similar to the derivations which we have calculated to the inductance. That's why I will not go to the derivations again. You can check over it. I have given it in a tabular form. I will maximize or zoom it like this. Now, the tabular comparison of inductance and the capacitance calculations. Configuration is the single phase two-wire line. Inductance L, Henry per meter is the unit. Capacitance C, Farad per meter is the unit. So single phase two-wire line, it is 2 into 10 to the power minus 7 ln of d by r dash. But in case of capacitance, it is 2 pi epsilon ln of d by r. Please try to make the difference that in case of inductance we used r dash, but here it is not r dash, it is directly r. There is no 0.7788 r, there is directly r. So three-phase line with unsymmetrical spacing. So 2 into 10 to the minus 7 ln of d equivalent by r dash. Here also it will be similar, 2 pi epsilon divided by ln of d equivalent by r. D equivalent will be equal to cube root of d12, d23 and d31. Composite conductor lines, 2 into 10 to the minus 7 ln of dm by ds. Here also it is 2 pi epsilon ln of dm by ds, where dm is equal to mnth root of daa dash up to dam dash dash up to d and a dash dash up to d and m. These are the mutual distances between the two conductors. Similarly, ds will be equal to n square to the root of daa dash up to dan. So finally it will be up to dna dash up to dnn. These are the self distances of all the conductors from its own subconductors or substrands. Bundle conductors 2 into 10 to the minus 7 ln of dm by ds, it will be similar, 2 pi epsilon ln of dm by ds, where dm is same as above. ds is r dash into d for inductance. When we have two conductors, two subconductors, and it will be capacitance, it will be square root of r into d. Similarly, it will change if we change the configuration, because I have assumed here only two subconductors. If we have three subconductors, it will be cube root of r dash into d into d. Here it will be r into d into d, cube root of r into d into d. Similarly, for a three-phase double circuit line, it is 2 into 10 to the minus 7 ln of dm by ds. Here also it will be similar, 2 pi epsilon ln of dm by ds. Here dm will be equal to cube root of dma into dmb into dmc. ds will be equal to cube root of dsa into dsb into dsc. It will be, this dma will be identical in both the cases, but ds will be slightly different. dsa is equal to dsc. We have seen this, they are symmetrical with respect to each other, so they will be equal. R dash into daa dash for inductance, for capacitance will be equal to r dash r into daa dash for capacitance, because there will be no r dash. dsb will be equal to r dash into dbb dash for inductance. calculation for capacitance calculation to be equal to R into d dV dash. So let us try to find out use the same thing to find out the capacitance of different configuration. So let us try to see this. Determine the capacitance and the charging current per kilometer of for the following system of 220 kV and 50 Hz. This is very simple to find out the charging current. You can see this. You will see that how we will be using this. So the configuration is we have this is phase A, this is phase B, this is phase C. They have two subconductors which are placed apart from each other 0.4 meter, and the phases which are apart from each other 5 meters each. The diameter of the each strand or each subconductor is 15 mm. So first we will calculate ds, which will be equal to dsa, because dsa in this case will be equal to dsb will be equal to dsc, and ds will be equal to cube root of dsa into dsb into dsc. So finally, since they are same, it will be equal to dsa. That in this case will be equal to r into d, not r dash. I am repeating again, it will be r into d, where r is this 15 into 10 to the power minus 3 divided by 2 to convert this diameter into radius into 0.4. It comes out to be 0.05477 meter. So dm will be the uh, equivalent distance, mutual equivalent distance, that will be equal to distance between these two, that is 5, the distance between these two, that is 5, and distance between these two, that is 10. 5 into 5 into 10, this will be also equal to cube root of 2 into 5. It comes out to be 6.3 meter. I have explained in the previous class that how we have reached to this type of formula instead of the actual formula, which was that is different distances from this to this, and then from this to this, and then from this to this. We have finally come to this formula, and we know that when d is greater than this small d, we will be using this formula. If that d is not very large as compared to this small d, then we will not be able to use this type of formula. So finally, capacitance will be equal to 2 pi epsilon ln of dm by ds. 2 pi epsilon is 8.85 into 10 to the minus 12 ln of 6.3 divided by 0.06477 farad per meter. So it comes out to be C will be equal to 1.17185 into 10 to the power minus 11 farad per meter. This is the answer for the capacitance. The charging current per phase will be equal to j omega v into c, or j omega c into v. So j is as it is, omega is 100 pi for 50 Hz frequency. Per phase voltage will be 220 by root 3 kV. kV we have calculated this converted to volt by multiplying it 10 to the power 3, and this is the value of the c. So it comes out to be 4.676 into 10 to the minus 4 per meter, ampere per meter. It should have been ampere over here, ampere per meter, because we are using here capacitance per meter. This comes out to be ampere per meter. So here this comes out to be, when we change it into per kilometer, because we are perhaps yes, here you can see we have to find out the charging current per kilometer. So charging current per kilometer will be, we have to multiply it by 10 to the power 3. It comes out to be 0.4676 ampere per kilometer. So this way you can calculate this capacitance as well. This is very similar to that of the inductance. Only thing is you have to change the formula. Rest is almost same to calculate dm. dm will be identical, but ds will be slightly different, because of here we use the r instead of r dash. Now let us try to do one more numerical. This is the three-phase double circuit line, which we have already discussed in the class, but here in the class we have calculated the inductance. We will here calculate the capacitance. Again, that I is same, 2.535, r is 1.266. dm I will not calculate here, because dm we have already calculated to be equal to 6.611. Please refer to the value of dm which we have calculated in case of inductance. It will be same. Now this daa dash will be the distance of this daa dash. So it will be calculated from the Pythagoras term. This distance is 8 meter, because this is 4, this is 4. This distance is 7.5 meter. So daa dash will be square root of 8 square plus 7.5 square. It comes out to be 10.965 meter. I only calculated this because I require only this. Otherwise, for dm I have to calculate ab, dab, da dash, dab dash. These two also have to be calculated. So since we have already calculated this dm, so I need not to calculate this. So finally, this DSA is equal to DSC will be equal to 1.266 into 10 to the power minus 2. This is R into D, the distance between A and A dash, that comes out to be 10.965, that is total 0.37258 meter. So DSB will be this R is same value multiplied by the distance, that is 9 meters. It comes out to be 0.3375. So finally DS will be equal to, it should be cube root of, this will be cube root, I have forgot to written over here the cube root of 0.3725 square into 0.33755, it comes out to be 0.36051 meter. So to calculate this C, we use this formula 2 pi epsilon divided by ln of dm by ds. 2 pi epsilon is the constant one, ln of 6.61 divided by 0.36051, it comes out to be 1.9115 into 10 to the power minus 11 farad per meter. We can use the usual units of it, microfarad per kilometer. In case of inductance, it was millifarad per kilometer. It is 0.01945 microfarad per kilometer. So I will give you one homework numerical. It is like this: find out the capacitance of the line as shown in the figure. The radius of each subconductor is given to be 1 centimeter, and the distance between subconductors is 0.6 meters. You need to calculate first dm. Dm will be very simple. It will be cube root of 2 into 6, and then ds will be equal to square root of 6 into this radius, that is 1 into 10 to the power minus 2. After that, you can use the formula 2 pi epsilon to the ln of dm by ds, and that will give you the capacitance. Today I will stop over here. I think this is enough. So please try to feel free to ask me questions if there are any regarding this class. Thank you.